Heat transfer, generalized thermal resistance network. So in this lecture, what we're going to do is we're going to extend our analysis to cover uh, not only series networks, but parallel networks for heat transfer. So let's take a look at the following situation. We have one material on top of another material. Uh, so in this kind of situation where these can be treated as resistors in parallel. So for example, if we start here on this side at T1 on the left hand side, and we're going to go to T2 on the other side, these are not in series; they're in parallel. So we simply make our assumption that we treat each one of these as a resistor, and then we find the total resistance like we do for parallel resistors. So 1 over R total is 1 over R1 plus 1 over R2, and if we just have two of them, we can just multiply and divide them by the sum. So Q dot is delta T over R total for this situation. So if we have a situation where we have uh, two materials on top of each other and they're combined with a material on the right, then we treat these two materials as parallel and they're in series with this third material. So it's very easy to extend this exactly. We find the total resistance. So R12 is here's the combined resistance of those, and that's added to R3. And then if we have a you know a convective area from this guy here convecting out to some fluid, we actually add in a R convection. So in each case, we can write the individual resistances for each of the areas. So let's look at a more complicated example of heat loss through a composite wall. So this wall is 3 meters high and 5 meters wide, and it consists of long 16 centimeter by 22 centimeters cross-sectional area horizontal bricks with a given K value. They're separated by 3 centimeter plaster layers. So this shows the plaster layers. So the brick is embedded and it has plaster all the way around it. There are also 2 centimeter plaster layers on each side of the brick. So not only are the bricks have plaster between the bricks vertically, it also has plaster between the horizontally that separates the foam and the outside. So the indoor and outdoor temperatures are 20 degrees C and minus 10 degrees C respectively. So here's the outside at minus 10 degrees C and the inside is 20 degrees C. And the convection transfer coefficients on the inner and outer surfaces are given as H1 and H2. Assuming one-dimensional heat transfer, disregarding radiation, determine the rate of heat transfer through the wall. So here, to treat this as an electrical network, we're going to have to be kind of careful here. We have to go step by step. We're going to have for the inside, we're going to have an R value that we can calculate. We can calculate R1, which is the resistance value for the foam. We can calculate the R values for the side plaster here and here. And then we can calculate the R values for the plaster in the center, the R value for the brick, and finally the R value for the convection out to the outside. So here we have to treat these values for R3, R4, and R5 as in parallel, and the other resistors are going to be in series. So first we calculate the equivalent resistance for the three resistors in parallel in the middle. So we got R3, R4, and R5. So based on the values on the previous slide, we can calculate the equivalent resistance for the three resistors in parallel, and then we can find the total resistance by just simply adding all the resistances up. So we get 6.87 degrees C per watt. So finally, we can calculate the heat transfer rate, Q dot. It's delta T divided by R total. We get 4.37 watts per 0.25 square meter surface area. So we divide the 4.37 watts by 0.25 meters squared, we get 17.5 watts per square meter area. So the total area of the wall we're told is 3 meters by 5 meters, which is 15 square meters. Then we can calculate the rate of heat transfer of the entire wall simply by multiplying the 17.5 watts per square meter by 15 square meter. We get 263 watts. Of course, as the book points out, this result is approximate since we assumed the temperature within the wall to vary in one direction only and ignored any temperature change in the other directions. Well, that's the end of this lecture. I'll see you in the next lecture.